Okay, good morning. Now we're gonna continue still on the same lesson, chapter 5, lesson 4, and the title is Riemann sums and the definition of definite integral. You can open your book, page 206. Page 206, okay? On the previous video, on the previous lesson, the main important thing that you need to keep in your mind is the mathematical definition of definite integral. Yeah, I will write it again one more time. The mathematical definition of the definite integral. The integral of fx dx from x equals a until x equals b is equal to the limit of n approaching infinity of b minus a over n. Yeah, and then multiply by sigma from I equals 1 until n of f of ci. Yeah, and this definition is approached by using a Riemann sum method, which is actually, if you want to see in your book what is Riemann sum, page 205 on the below the definition. Riemann sum is an approximation of the definite integral of fx with respect to x on the interval from A to B using rectangles to estimate areas. So we are using rectangles. Yeah. So today, like I said, I want to teach you how to approximate the value of definite integral. Again, the estimate, yeah, not yet finding the exact value, but to estimate the value of definite integral using Riemann sum method. Yeah. Before I start, there are 5 types of Riemann sum method based on the method to take the sample points. Yeah, there are 5. The first one is left Riemann sum. The second one is midpoint Riemann sum. The third one is right Riemann sum. The fourth one is upper Riemann sum. And the last is lower Riemann sum. So there is the left, midpoint, right, upper, and lower. And these 3 you can see on figure 5.4c. Okay, now look at your book, page 206, figure 5.4c. So what's the difference between those 3? The difference is just the matter of where you take the sample point of each rectangle. Yeah, you see there are 3 graphs with the same function, figure 5.4c. There are a function in between A and B. It is partition into 6 increments, yeah, into 6 sub-interval. Oh, by the way, all of this method, we're gonna assume that the delta x is the same. That all of the width of all of the base of each rectangle is made the same. So it's equal base. Yeah. So that's why you see on the figure that's from A to B there are 6 rectangles and they are all having the same base. Okay, so there are 6, and you see the left Riemann sum. It means that the sample point is taken from the most left of the rectangle. It means from the left part of rectangle, left part, left part, left part, left part, left part. Yeah. Well, maybe I will draw one so you understand more. Let's say I'll just do it. So from A until B. And then let's say I have 4 partitions, yeah? Let's say I have 4 partitions. It means there are 4 rectangles, right? There are 4 rectangles. And the sample point that I'm gonna take, if it is left, then it's always from the left. So this is the first one, this is the second one, this is the third one, this is the fourth one. I don't use this one. Okay, so the rectangle will always be like this one, and this one, and this one, and this one. Okay, so it means that I'm taking it from the left, from the left, from the left, from the left. Yeah. And then the second one is the midpoint. If it is the midpoint, then it means that I'm taking the sample point from the midpoint in between on the mid of the rectangle. So middle, 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 middle. So this is my rectangle, this is my rectangle, rectangle, and this is my rectangle. Yeah. And then if it is the right, then I take it from the most right. I take it from the most right. Take it from the most right. Then I'm taking it from here, from here, from here, from here. So it's gonna be this one. So it's gonna be this one, then this one, then this one, and this one. Yeah. So that's the three, which is you can see clearly in figure 5.4c. Yeah. And then for the upper and the lower Riemann sums, you can see on the figure 5.4d. Yeah. So the sample point is taken not based on the position of the x, whether it's on the left or the right or on the midpoint, but it's based on how low, what's the minimum height for lower, and what's the maximum height for upper. Yeah. So if you see on your book figure 5.4d, for the lower one, it doesn't matter where the x, but you have to look at, you have to take the sample point that makes the rectangle the lowest, but still touching the graph. Yeah. So if I try to make it here, if I try to make it here, I will. This is. And then I will draw it here, and then I divide into 5 partitions, 4 partitions. This. Okay. So it doesn't matter the position. It doesn't matter the position of the x, whether it's on the most left or the most right or on the midpoint. But I will always take the sample point that still touch the graph, but it's in the minimum value of the fx, of the y value. Yeah. So for the first, so let's all just do this one, the partition first. So it means that if it is lower, then the first one will be here, will be here, will be here, and will be here. So this is the sample point 1, this is sample point 2, this is sample point 3, and let's say that this is the sample point 4. Okay. And if it is upper, then I pick the sample point where it still touch the graph, but it's in the highest. So it's this one. So it's this one, this one, and this one, and this one. So for the second one, then it's gonna be here. This is the sample point. Yeah. So basically, for the lower Riemann sums, you will always underestimate. It means if you use lower Riemann sum, the area that you approximate will be always lower than the exact one. And if you use the upper Riemann sum method, then the area that you estimate will be overestimating the exact area. Okay, so those are the 5 ways how to pick the sample points using Riemann sum. Okay, now I'll give you example how to estimate it. I will use the equation in example 1, but I will change the instruction. Yeah, for integral 1 until 4, 1 over x dx. Yeah, the instruction is to estimate. The instruction is to estimate. Oh, by the way, usually, if you want to use this method, usually the one that is used is this tree. Yeah, or this two is rarely used to estimate the area below the graph. Usually, it's this tree. And for me personally, I prefer to do the midpoint, but you have to be able to do all of them. Yeah. So let's see, 1 over x, let's say estimate with the n equals 6, in which there are 6 increments, there are 6 rectangles, yeah. And like I said, the delta x is the same, the base of each rectangle is the same, that it means that the delta x is equal to b minus a over n, and in this case, it's equal to 0.5. Yeah, 0.5. So if I draw a one-dimensional number line from 1 until 4, and I define to 6, it means that it's 1.5, 2, 2.5, 3, 3.5, 3.5, 3.5, and 4. Okay. Now, basically, if we take the definition, then actually the area is approximated by this one, right? The sum of the area of rectangles is that one. So the area is approximately b minus a over n times sigma notation of f of ci equals 1 until n. Yeah. So in this case, it's gonna be 0.5 times f of c1, f of c2, c2, f of c5, f of c6. Yeah. And the fx, in this case, the fx is equal to 1 over x. Okay. Now, if we want to use left, if we want to use left Riemann sum, then actually we take it from here, 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 right? We take it from the left. So it means that it's approximately equal to 0.5 1 over 1 plus 1 over 1.5, 1 over 2, 1 over 2.5, 1 over 3, and 1 over 3.5. Yeah, because we take from the left one. Now, how about the middle one with the midpoint? Then if we do the midpoint, then it's still the same, 0.5, but the multiplication is midpoint. What's the value in between 1 and 1.5? 1.25, of course, right? So the fx is 1 over x, so it's going to be 1 over 2.25 plus 1 over 2.10. Never mind. It's supposed to be 1.75. 1.2.25, 1 over 2.75, 1 over 3.25, and then the last is 1 over 3.75. That's if midpoint. Yeah. How about the right? If we take the sample point from the right, then it's approximately equal to 0.5. Then we take the left one. So this one, 1, 2, 3, 4, 5, 6. Yeah. So it's equal to, so instead of 1, if left start with 1, C1 equals 1. If right, C1 equals 1.5. Okay. So that's how you do the Riemann sums. That's how you use the Riemann sum to approximate the definite integral, the area below the graph. Okay. Thank you.